Okay, so the first TD learning algorithm that we're going to cover is called Sarsa. The name is just the extended transition, right? State S, action A, reward R, next state S, and then we add another action to the next states. That's why it's called Sarsa. This is the first, as I said, the first TD learning algorithm that we're going to cover. So here we sample, again, a full transition from the environment, but then we also sample the next action from the policy that we are currently using. This is why this is known as an on-policy algorithm, similar to the Monte Carlo approach that we've seen previously. The learning is sensitive to the algorithm, to the way that we are behaving in the environment. So we perform a Bellman update. We only eliminate the max operator, right? We choose a specific action from our current policy. And then we do the update based on that. Sarsa is guaranteed to converge on the optimal policy eventually, given that we're performing infinite often visitation. That is, when we're performing sufficient exploration in the state and action space. And of course, as long as we converge at the limit, or we converge on a greedy policy eventually. So this is the pseudocode for Sarsa. It's a pretty simple algorithm. So as before, I'll ask Vav to quickly go over the demo, and I'll try to provide feedback as needed. And it's a simple domain.
Alright, hello everyone. Like we can see on the bottom left, we have our domain with the state space XYZW and our actions. And we shall take an initialized queue function, initialize all zeros for each action in each state. And we'll go over.
So the all zero initialization is not required, right?
Yeah, it's a random initialization. In this case, 0.
Arbitrary, not random.
Yes.
It's slightly okay.
We take our arbitrary assign queue function. We take it for each state. We take an action A. So in this case, we start with state X. Take action left. Go to get a reward of 0. Reach state W. And at which point we again have to see what is the best action to take in the next state, which in this case would be null, as W is a terminal state.
So again, not necessarily the best state, we didn't define that, but the state according to our current policy.
According to our current policy.
Right, I think we're just using epsilon greedy, but yeah, you can have several options there.
Yes. So we take the action in the state, observe the reward, and update our queue values, using the TD learning queue update function, the Bellman update, and we see. So here the queue value for state X taking left remains 0, and then we repeat this for the remaining states. So now we go to state W, see the take action exit. Get a reward 0, continue staying in W because it's a terminal state, and we continue this for all states. Here we get an updated Q value of -100 for W. And we repeat this for again. So last time.
So we exited.
We actually came out of the loop.
Yeah. So
yes. So
we start a new episode.
Yes. So this episode is over. Yes, because we reached state W, we reached the end of the episode. We exit this loop, and
so TR means terminal. Okay?
Yes.
So S prime is terminate.
Now we go back to the outer loop. Initialize the state first initial state again. Go collect an episode once more. Starting from state S again, we this time see a reward of -100 going to taking the same action left instead of seeing the reward of 0.
Can you move a bit out of the correct?
So This time, yes, taking action left in state X gave us a reward of minus 100. And upon updating its Q values, this time we get a value of minus 90 for action left on state X. And we continue this for the rest of the
Okay, you see that this is unlike the Monte Carlo approach. Here we do TD learning. We propagate values from immediate neighbors, so it takes time until the value propagates back to X, for instance,
yes.
to state X.
So for in the Monte Carlo, that we might have learned the value for X in the initial episode, but it might take more episodes for TD learning.
Right, and this is something that we've discussed previously, right? The balance, the difference between TD learning and Monte Carlo approach, the bias versus variance. Okay, so this also exists here. I would say this is the other extreme of from the Monte Carlo example or the Monte Carlo algorithm. This is the other extreme, one-step TD learning. Later on, we'll see how we can bridge these gaps. If we can define algorithms that somewhere in the middle or that have a continuum. It can do one-step look ahead or more than that, right? Or something more dynamic.